Hello friends, this lecture is basically for physics students who are doing a PG course in microprocessors and microcontrollers. We'll begin by taking a survey of the different topics to be covered in this lecture series. In this lecture particularly, we are going to study the PIC microcontroller 16F877. Particularly, we'll discuss its features, pin signals, and its memory structure in this particular lecture.
These are the 4 units which you are supposed to study. In unit 1, we are going to continue with the study of PIC microcontrollers. Right? PIC-16F8XX. Actually, one more X is needed here. 8XX flash microcontrollers. Okay. So in this unit, we are going to continue the study of PIC microcontrollers. In the last semester, in the last unit, you got introduced with the PIC microcontrollers, and there we have studied the basic family member of PIC microcontroller, which was 16C61 or 71. Here we are going to study the highest level family member of this microcontroller family. Okay, particularly we are going to study in details PIC 16F877 microcontroller. XX means here there are 2 digits, X and one more X. There are 2 digits, and those digits may be different digits. So the highest family member is 16F877, and that we will be studying in details in this unit. So that will actually complete the study of these flash microcontrollers. Okay, unit 2 is about interfacing microcontroller and PIC microcontrollers and industrial applications of microcontrollers. Because we have studied different kinds of microcontrollers, now we are supposed to study how they are used in industries. What are the different actual applications of these microcontrollers? So unit 2 is devoted for that kind of study. That means when you have a microcontroller, you need interfacing of the different devices with the microcontroller. Microcontrollers are typically used to control the different devices. Maybe it may be a motor, it may be a relay, it may be some electronic circuit. Okay, so you may connect some sensors to the microcontrollers. So how the interfacing can be done, and what are the various applications which are actually implemented in the industrial environment, that we are going to study in unit 2. Okay, so that will actually complete the study of microcontrollers. We will be studying basic microcontrollers and their applications. Then in unit 3 and 4, we are going to get introduced with the microprocessor, which is a 32-bit microprocessor called as ARM processor. We are going to study ARM7 microprocessor, which is a 32-bit microprocessor. In unit 3, we will study the hardware section. We will study the actual chip IC and its internal architecture, and in the next unit, unit 4, we will study the programming of this microprocessor. So actually this ARM processor is the processor which is currently used most popularly in the high-end computerized or electronic embedded systems. Okay, and therefore it's very much essential to understand the working and the programming of this microcontroller. Okay, so after in the last semester, as you know, we have studied 8085, which was 8-bit processor, then 8086, which was 16-bit processor. Now in continuation with that, here we are going to study 32-bit microprocessor, ARM processor. Is it clear? So that is the overview of the different topics to be studied in this paper. References are shown here. Okay, the main reference for first 2 units is only your A.V. Deshmukh, Microcontrollers, Theory and Applications by A.V. Deshmukh, the same book that you used in the last semester for some of the topics. Chapters are specified, chapter 10, 11, maybe 12, 13. One more book which may be required here for some of the topics of this unit is 8051 microcontroller and embedded systems by Mazidi and Mazidi. Okay, one or two topics from this unit are taken from this book. And then for ARM processor, there is a separate book called as ARM System on Chip Architecture by Steve Faber. Okay, so these are the books. So once again, definite references are provided. Actually, specific chapters are also mentioned, which are relevant to your syllabus, and this is the syllabus of this paper. ठीक है? Is it clear? काय शंका असेल तर बोला. Shall we continue? Okay. So today we'll begin with this unit 1, which is about PIC-16F877 flash microcontrollers. This table gives the survey of the family members of this PIC microcontroller family which are lying at the highest level. Okay, this table shows actually the features of in all 4 different family members which are lying at the highest level in their family. They are having maximum possible features. Actually 16F877, this IC PIC microcontroller has topmost features, highest level of features. Okay, then below that with little lower features you have 876 with some still more lower features 874, and at the lower level it is 873. Okay, but all these 4 devices, they are lying at the top of this family of PIC microcontrollers, with this microcontroller 877 having highest or maximum features. Let us see the features of this highest level microcontroller 16F877. You can understand the terminology here because we have already studied microcontrollers to a great extent up till now. You know, it is operatable with DC to 20 megahertz. You know, it's a speciality of these PIC microcontrollers that you can reduce the frequency of operation to a very, very low level. Even your clock frequency can be in kilohertz. Even it can be in hertz. It is possible. So almost DC level to at the most 20 megahertz is the operating frequency of this microcontroller. Program memory is 8K cross 14 words. You know that in PIC microcontroller the program memory is 14-bit wide. That we have studied last semester. 14-bit wide, because every instruction of this microcontroller is 14-bit wide, and one instruction is accommodated in one location of the program memory. Okay, so the program memory is 14-bit wide, and such 8K locations are there in the program memory. So 8K cross 14-bit program memory. Then you see the data memory. Data memory is about 368 bytes of RAM. Actually 368 cross 8 bits पाहिजे या ठिकाणी. It's not bytes, or it is 368 bytes of RAM. Okay, 368 bytes of RAM, and additionally it has 256 bytes of EEPROM in the data memory. In the PIC microcontrollers that we discussed last semester, only this RAM was there, smaller amount of course, but only this type of RAM was there, which is volatile memory. You know, readable, writable, but volatile. Volatile means as soon as see it is used for temporary storage of data during execution of the program. Okay, when you switch off the power supply of the microcontroller, the information in this memory will be lost. In that sense, it is volatile type of memory, data memory. In this device, that type of memory is available with higher size. In addition to that, 256 bytes of electrically erasable programmable read-only memory is also available as a data memory. That means similar as your program memory, which is permanent memory. Once the program is loaded into the chip, even you switch off the power, the program is not erased. Similarly, some part of this data memory is in the form of this EEPROM, which is non-volatile memory. Non-volatile memory. That means it is possible that during program execution, you can store data in this. You can read the data from this. You can perform read and write operations similar as you do with this. But the additional property of this memory is that even you switch off the power, the information is not lost. Information is not lost. Okay, so that is an additional advantage provided in this chip. For example, suppose you want to keep some parameters. You want to maintain the tables of the different parameters, maybe process parameters, which are required for operating a given process through the program. So those parameters can be saved in this memory. So even you switch off the system, the parameters will remain intact. Okay, and also it is possible that it is possible to change the parameters in the later course of time. Okay, so it is possible that you can change the parameters and or modify the parameters also. Okay, so that's how this data memory is available in these two parts. Then if you see the timers, it has 3 timers plus watchdog timer. Watchdog timer is one of the additional type of timer, as you know, in PIC microcontrollers. It is used to keep a watch on the proper operation of the microcontroller, that is there. But additionally, there are 3 timer counters. If you remember, in the lowest device 16061, it was only 1 timer available in that microcontroller. That was timer 0. Okay, but here there are total 3 timers available. Then IO ports, you can see that there are in all 5 IO ports. 16061 or 71 had only 2 ports. One was 8-bit port, other was 5-bit port. But here it has 5 ports with 25 milliampere current sourcing and sinking capacity. Okay, and there are number of additional features which are listed here. This microcontroller additionally contains 8-channel 10-bit A to D converter. So ADC is inbuilt, and it is 10-bit ADC and having 8 channels. So it is possible that you can connect 8 different input devices, analog input devices, to this microcontroller, and you can convert the analog input from each of that device into digital equivalent, and that can be processed further. Okay, so you don't need you don't have to use separate IC for an ADC. This microcontroller itself contains ADC. So this feature is not available anywhere in your microcontroller 8051. None of the 8051 device has an ADC. Okay, but PIC microcontroller has ADC, 8-channel 10-bit ADC. Then additionally, it has serial ports. 2 serial ports are available. You know, 8051 microcontroller had only 1 serial port, but this has 2 serial ports. It can communicate serially with 2 devices at a time. It also has a parallel slave port, PSP it is called as. The data can be sent parallel. It can be inputted or outputted. Okay, one more important feature that this has is it has 2 compare capture PWM modules. Okay, there are 2 such identical modules. Each module is called as CCP module. C for capture, C compare, and P for PWM. So there are 2 such identical modules called as 2 CCP modules, CCP1 and CCP2 for example. And these modules are provided to provide some additional features, additional advantages, benefits while doing the interfacing. Many times you need to generate a pulse width modulated waveform. For example, if you want to control the speed of a DC motor, then you need a PWM type of signal to be supplied to the motor. We will discuss that in details later. So the speed of a motor can be controlled with the help of pulse width modulated signal, and that can be directly generated by this particular module. You don't have to write separate program for that. Okay, and there are some capture features, compare features. We will discuss this in details. But that provides some many additional applications because of availability of these 2 modules. The microcontroller has some additional applications. Okay, and it can be used over a wider range of applications. Okay, so these are the additional features you can see. Otherwise, the BOR, POR, brownout reset, this you have studied in 6.1. Power on reset, all these features are still available here. The voice of timer is there. Okay. Very important feature of all these family members is that all the family members have same set of instructions. Okay, the instruction set is only made up of 35 instructions. As you know that PIC is a RIC type of computer, reduced instruction set type of computer, and therefore very small number of instructions, and the same instruction set is applicable. Whatever, that means whatever program you run with 16661 can be executable. It is executable with any of these family members because the instruction set is same. That's what they have maintained. Is it clear? These are the features of this highest PIC family member. This member we are going to study in details in this unit. Is it clear? Okay, now if you compare the other devices, which we may call as lower devices as compared to this, you can see what modifications are done. For example, if you go for C876 microcontroller, this was 877, one step lower, 876 microcontroller, you can see that it has same program memory, it has same data memory, same number of timers. The only thing is that the number of IO ports is reduced. Here you can see that there were 5 input-output ports. Here there are only 3. Okay, because of that, what happens? When there are more number of IO ports, you need more number of pins for the IC. Because every port, suppose it's an 8-bit port, then it will require 8 pins to input or output the data. So larger the number of ports, larger number of pins are required. Smaller the number of ports, smaller number of pins will be required. And therefore, you can see that 877 is a complete 40-pin IC. The size is same as the size of your microprocessor 8085 or 8086, 40 pin IC, but this IC is of smaller size. It is hardly 20 pin IC because the number of port pins is reduced. Okay, so when you want to, in your application, if you don't need more number of ports, then you can use a IC which has smaller size. Okay, so while designing an application, you can reduce the PCB area. You can make the circuit more compact by using 876 rather than 877. Okay, so that's the idea, and that's why the size is smaller. Otherwise, the features are similar. Only thing is that instead of 8 channel, it is now 5 channel because number of pins is now reduced. You cannot provide 8 pins to carry the 8 analog signals. Only 5 pins are possible. Okay, otherwise the features are identical. Okay. Next you go for 874. In the 874 chip, what you observe? The size of the memory is reduced. Now it is 8K, it is 4K only. The RAM was 368 bytes RAM, now it is reduced to 256. And 256 EEPROM is reduced to 128. So amount of memory is now smaller. Otherwise, timer section, number of ports is same as this. They are identical with your highest device, and therefore all the remaining features are similar. The only thing is that the size of memory, amount of memory is smaller. So in your application, if you need more number of ports, you want to connect more number of devices, but amount of memory may be smaller, then instead of going for this IC, you can go for this IC. It will be cheaper and it will consume less power. Okay. When you go to the last device, which is 873, you can see that in this device the memory is also reduced as compared to the highest device. You can see 8K is reduced to 4K. Memory is similar to this, it is reduced. At the same time, the number of ports is also reduced. Okay, so this particular IC is identical to 876 in terms of ports, and it is identical to 874 in terms of memory. So memory as well as number of ports is reduced. Okay, so again you can have an application where you don't need many ports and also you need small amount of memory, then you can go for this IC. The size of this IC will be smaller. Okay, so that's how different combinations are provided in the different ICs. All these ICs are available in the market. As a designer of the circuit, you have to choose the proper IC for your application. Is it clear? So let's go to the next topic. Now we are going to study the highest device in with all the details. So highest device is 16F877. This IC is shown here. You can see it is a 40 pin IC, and these are the pin signals. PIC microcontroller 16F877. If you see the pin signals, there are two different signals are written for every pin. So that means that pin has alternate functions. Basic function of this pin is RA0, and AN0 is the alternate function. Right? For example, this is RA0 means is port A pin. Port A pin. RA0, RA1, these are port A pins. Okay, and they have got alternate function of carrying analog signals, AN0, AN1. There are 8 analog input channels. So those are the alternate functions of these pins. So different pins have different alternate functions. Some of the pins, they don't have alternate functions. That's all. Okay, so that's how this IC has different pins and pin signals. If you consider the number of ports that this IC has, this IC has in all 5 ports, as we have mentioned before. This IC has in all 5 ports. It is port A, port B, port C, port D, and port E. Out of these ports, port A is a 6-bit port. Port B, C, and D are 8-bit ports, whereas port E is only 3-bit port. So you can see that 6 plus 3, 9 plus 8. Actually, how many port pins will be there? So these are 6. This will require 6 pins. This will require total 24 pins, 8 into 3. And this is 3 pins. Okay, so total number of pins which will be used up by these ports will be 33 pins. Your IC is 40 pin IC. Out of these 40 pins, 33 pins are used up for IO ports. 33 pins for carrying IO ports. Okay, if you see in that diagram, you can understand that there are 4 pins available for connecting power supply. 4 pins for connecting the power supply. Actually, for power supply you require 2 pins, VCC and ground. But in this IC you will see that 2 pairs of pins are provided. 2 pairs of pins are provided for supply. So it is VDD and VSS one pair, and VDD and VSS another pair. So VSS is actually ground and VDD is the supply pin. Okay, purpose of providing such 2 pairs is that you can apply the power either through this pin or through this pin. Okay, so they are particularly provided on both the sides of this IC. This is for convenience of PCB designing. If while designing a PCB, if the power supply lines are coming from this side, then you can use these pins. If the power supply lines are coming from this side, then you can use these pins. You don't have to take the connections all the way across the IC. Okay, so that's why these pins are 4 pins are provided. So 4 pins are for power supply. Okay, then there are 2 pins for oscillator connections. There are 2 pins for connecting the crystal, for crystal connection. As in case of any other microcontroller or microprocessor, the clock oscillator circuit is inbuilt. You have to connect the crystal from outside, and the 2 pins are provided for that. And there is one pin which is called as master clear pin, which is actually the reset pin. Master clear pin. Master clear. Okay, so that totally comes out to be 40 pins. Okay, so if you consider this IC, then out of 40 pins, 33 pins are carrying ports. You can say most of the pins are carrying ports: RA4, RA5, RE, RE0, port E. And this is port C, RC2, RC3. This is port D, right? This is port C. So most of the pins are used for carrying the IO ports. Okay, 4 pins for power supply, 2 pins for connecting the crystal. You can see here, pin number 13 and 14 are for connecting the crystal, and one is master clear pin that can be seen somewhere. This is the master clear pin, pin number 1. Okay. Okay. Now let us go inside this chip and try to understand the different internal functional blocks. We'll begin with the memory section. As we have seen in this table, that this IC has 8K cross 14 program memory and 368 bytes and 256 bytes of data memory. So let us begin with the program memory. It has 8K cross 14 bit program memory, right? I am talking about the program memory. It is 8K cross 14 bit. So as you know that the program memory is 14 bit wide, and there are 8 kilo locations. So such 8K locations. So that's how it is organized. And every instruction of this microcontroller is 14 bit wide. So it can hold one instruction in one location. Instruction 1, instruction 2, instruction 3, and so on. Address map goes from 0000 to, it is 8K locations. So it will be a 13-bit address, and that goes up to 1FFF. 1FFF. 1FFF is 13-bit address. Right? 4 into 3 plus 1, so 13-bit address, because 2 raised to 13 gives rise to 8 kilo. So to address 8 kilo locations, you need a 13-bit address. And that's why the address map of the program memory is from this to this. So the program counter of this microcontroller is 13-bit wide. You know this. Program counter is 13-bit wide. So because this address will be held in the program counter during execution of the instructions. So this shows the program memory map. Details of that. Just now we have seen that this program memory is 14-bit wide. So this is 14-bit wide, and there are 8K locations going from 0000 to 1FFF. Okay, 0000 is said as reset vector. Vector means the address where the execution is transferred when that particular event occurs. That means when you reset the microcontroller, the execution will be transferred to this address. That's why it is a reset vector. This is the reset vector. Secondly, there is an interrupt vector, 0004 interrupt vector. That means when any interrupt occurs, the execution is transferred to this particular vector address. We have seen in PIC microcontroller, while discussing 16661 and 71 also, we have seen that different interrupts, they don't have separate vector addresses. All the interrupts have same vector addresses, and therefore whenever any interrupt occurs, the execution is transferred to this particular location. Here you have to check which type of interrupt has occurred, because different interrupts have different flags. Okay, interrupt flags. So whenever an interrupt occurs, that particular flag is set. So here you can write a program at this particular address. You can write a program to check the flags, and depending upon which flag is set, you can understand which interrupt has occurred, and depending upon that, the execution can be transferred to the corresponding ISR. So that's how this interrupt vector, single interrupt vector. And then you can divide the whole program memory into different pages. Okay, so there you can imagine that this 8K is divided into in all 4 pages. So each page is 2K page, 2K page. Okay, this is 2K, 2K and 2K, right? So 4K, 4 pages are there. So out of the 14-bit address, for example, it's a 13-bit address. So this is a 13-bit address. Out of this 13-bit address, you can imagine that first 2 bits will represent the page number, and remaining 11 bits will represent the actual address within that page, right? So 0, 0 up to, so see, this is address 0 to address 10, and address 11 and address 12 can be considered as page selection bits for page selection. Okay, and you can understand how this addressing will go on. So 0, 0, 0, so 0, 0 to 1, 1, all 1. So that will be page number 1, sorry, page number 0, then 0, 1, all zeros to all 1. This is page 1, this is 1, 0, and then 1, 1, with all bits 1. Right, so this address is your 1FFF. So that's how we can see that for highest to most significant bits can be used for page selection. Right, page 0, 1, 2 and 3. Okay, one more thing you remember that in a program counter, okay, so this address will be held in the program counter, right? So program counter is 13-bit wide. The program counter is 13-bit wide, and in this microcontroller, the program counter is available in the form of 2 registers. One is PCL, which is 8-bit, and other is PC latch, which is 5-bit. So that's how this 13-bit of program counter is organized. We have seen this while discussing the previous microcontroller. So these are the 13 bits, how they are accommodated. But out of these 5 bits, the highest significant 2 bits may be 00 or 01 or 10 or 11, as we have seen here, to select the page. Is it clear? Okay, so that is all about your program memory. Okay, now when you go to the next thing, it is about data memory. It is about data memory. Okay, let's talk about the data memory in short. as we have seen in this slide, that it has 368 bytes of data memory, 368 bytes of data memory, and 256 bytes of EEPROM. Okay, let us keep this EEPROM aside. Let us talk first of all about this RAM only. Let's talk about this RAM, because this is a separate type of memory. Okay, so let's talk about this RAM, which is volatile read-write memory. It's a read-write memory and volatile. It is like any memory in any other microcontroller, as we have seen, data memory. Even though it is said here that it is a 368 bytes of RAM, actually it is a 368 bytes of RAM which is actually available for the user. It is the RAM which is available to user. We'll see the total RAM which is available in this chip is 512 bytes. Bytes of RAM is available total. Out of that, only 368 bytes is available to the user. Other part of this RAM is used by the microcontroller or by the CPU for this operation. So let us see how this 512 bytes of RAM is organized. 512 bytes of RAM is organized. Okay, and out of that, how only 368 bytes is available to the user. So for that, you can see the memory banks. The 512 bytes of RAM is available in terms of 4 memory banks. 512 bytes of RAM is available in 4 memory banks. Bank 0, Bank 1, Bank 2 and Bank 3. Okay, to address 512 bytes, you require in all 9 bits. So 2 raised to 9 is 512. And therefore the address is 9-bit address. And that you can see here. Okay, so starting from the address 00, the address range therefore comes out to be 000H2 1FFH. 4 plus 4 plus 1, 9 bits. And this whole range is divided into 4 banks. Okay, you can see bank 0 contains address 00 to 7F. Actually it is 07F maybe. It is 000 to 07F. And then from 081, sorry, 080 here. Next address to 0FF is bank 1. Okay, so bank 0, bank 1 together is address having 00 to FF. So it is 256 bytes. Okay, so after 0FF, the next address is 100 to 17F, and then 180 to this. This totally comes out to be a total 256 bytes. So that's our total 112 bytes. Or every bank is having 128 bytes. Okay, so what you observe here is that your data memory, which is 112 bytes, is actually organized into 4 memory banks, and each memory bank is 128 bytes size. It contains 128 bytes, so into 4. banks. So that gives you 512 bytes. If you compare this with your 16061 type of microcontroller which you have studied last semester, then that microcontroller had only 256 bytes of RAM. So there were only 2 memory banks, if you remember. So these were available in 16C61. Okay, so there are 2 additional memory banks which are now available in this highest device. We'll discuss the detailed structure of these banks or different registers which are seen here. We can see in these banks, whichever registers are shown here are the SFRs, special function registers. These are seen here. Different SFRs are associated with the different functional sections, internal sections, maybe like timer section, port section, interrupt section, etc. And then some regions are available which are for general purpose use, general purpose storage. Okay, so the regions which are seen as general purpose storage, that total comes out to be 368 bytes. That's why it is said that the RAM which is available for user available for temporary storage of data is only 368 bytes. Okay, out of 512 bytes, this is available for the user. Remaining is used by the different SFRs. We'll discuss this in details next time.